In this lecture, we're going to continue applying the concepts of forces and Newton's laws of motion to various problems, both conceptual questions and numerical problems. Let's start with this one, which goes back to our discussion of static equilibrium. And as a reminder, static equilibrium is when an object is when an object is at rest, which means the net force, of course, acting on the object is zero. So you've got a ring seen from above, so you can think of this ring as being as placed on a horizontal on a table surface, and there are these two forces pulling it at some angle theta, and a force F pulling it in the downward direction. Question is, what is that magnitude of that force in terms of the other variables given in this problem? So here, again, it's a question of resolving forces. We want to focus on all the forces acting in the, let's say, the vertical direction. And what we have here is, let's call that the y-axis. And so the net force in the y direction has to be zero. Well, what are the forces? There are these 10 Newton forces acting up at an angle theta. So when you resolve them into components, you need to look at the y components of each of these forces. And if I just sketch the y components here, you will see that it's going to be 10 sine theta, or let's include the units here, 10 newtons times sine theta plus 10 newtons times sine theta. Those are the y components of those two forces, minus F is equal to 0, which implies, well, we can combine these two, which implies F equals 20 sine theta, of course, measured in newtons. And so the correct choice here would be E, 20 newtons times sine theta, or 20 sine theta, and measured in newtons, the unit being newtons. Here's another question. A box on a rough surface is pulled by a horizontal rope with tension T. The box is not moving. Box is not moving in this situation. And again, if you draw a free body diagram, you know what you have, you know the net horizontal force has to be 0. You've got the tension pulling to the right. There must be the frictional force acting in exactly the opposite direction, same magnitude as the tension, and in fact that force is going to be the force of static friction, and these two forces should have the same magnitude. So the correct response here is S is equal to T. F sub S is equal to T. And just put in one line out here. Not moving implies acceleration is 0, which in turn implies net force is 0. Here's another question. Again, box being pulled to the right at a steady speed by a rope that angles upward. So this makes an angle with the horizontal. The tension makes an angle with the horizontal. And in this situation, how do the forces, the tension, compare with the force of kinetic friction? And it's moving at a steady speed, which means constant velocity motion. Let me just say that this is a bit tricky. It is, you might say, well, it is moving at a constant velocity. Since it's moving at a constant velocity, means the net force must add up to be zero. And you might say, oh, because if that's the case, then the tension must equal the force of kinetic friction because it's moving. So since it is sliding, we are talking about the force of kinetic friction. You might say this has to be true, but actually this condition is not correct in this situation. Why? Because the tension is not in the same direction as the force of kinetic friction. What is true is that the net force in the x direction, if you're looking at the horizontal direction, the net force in the horizontal direction has to be zero. So again, which implies the net force in the x direction is zero, and also the net force in the y direction, but that's not relevant in this particular problem. Okay, so this in fact tells us that the x component of the tension must equal the force of kinetic friction. So it's not the entire tension that has to equal the force of kinetic friction, but it's only the x component. So this is T sub x has to equal the force of kinetic friction, which means that since it's only a component of the tension which has to equal the force of kinetic friction, the tension in this case is going to be, so the tension, the magnitude of the tension in this case has to be greater than the force of kinetic friction. Okay, so the answer here is T is greater than F sub K, because it's the x component of the tension which is equal to the force of kinetic friction. Just keep that in mind. Here's another question. Box is being pulled to the right over a rough surface. T is greater than F sub K, so the box is speeding up. So as you're pulling it, the tension is greater than the force of kinetic friction. Suddenly the rope breaks. What happens? So in this, once the rope breaks, you remember the tension essentially goes to zero, and what you have is the object is still moving at that instant. And if I draw the free body diagram, of course you've got the vertical forces, which are not quite relevant here, but we'll just put that just for the sake of completeness. There are these two forces. And there is now just the force of kinetic friction. And remember, the force of kinetic friction is a constant force. And so whatever there was before still exists. So there's the force of kinetic friction. There is the weight. And there is the normal force. And now the object is moving to the right. It's got some velocity. And there is a force which is now, that is the force of kinetic friction, which is slowing it down. So what's going to happen here is that as soon as the rope breaks, the object is going to start slowing down and eventually stop, because the force of kinetic friction still acts on the object. So it slows steadily and stops. Okay. Now, when you're deciding the direction of the force of kinetic friction, it is pretty straightforward, because the force of kinetic friction only shows up when an object is sliding on a surface, and it opposes the direction of motion. The force of static friction, on the other hand, can get tricky figuring out its direction. So remember, the force of static friction prevents an object from sliding on a surface. So in this case, you're looking at a truck which is accelerating in the forward direction. On the back of the truck is a crate which is moving, which is not sliding, which is moving along with the truck, which means it also has the same acceleration. Question is, what's the free body diagram of the box or the crate that you have in the back of the truck? The F sub G that you see in these sketches is just the weight or the force of gravity. Okay, so in this question, the way to think about this problem is, well, suppose there was no friction between the box and the floor of the truck. Okay, well, if there was no friction, as the truck accelerates to the right, the crate will just, or the heavy box is just going to stay in place. In other words, it's essentially going to be sliding from underneath the truck and falling off the truck. Okay, so if there was no friction, if you are focusing on the crate, it is as though the crate is moving in this direction, or for that matter, the truck is sliding from underneath the crate, or the truck moves in this direction. So friction, the fact that the only reason the box travels with the truck is because there is friction between the two surfaces, the bottom of the crate or the box and the floor of the truck. Okay, so you may be tempted to think that somehow the engine has something to do with the crate moving in the forward direction or accelerating in the forward direction, but no. The reason why the box travels with the truck is because of the presence of friction. If there was no friction, the crate won't move anywhere. It will just stay put. Okay, so in this case, what is propelling the box in the forward direction is in fact the force of static friction, which means the direction of the force of static friction is to the right, and that's what's providing the acceleration. So the correct sketch out here, the correct free body diagram in this situation is in fact C. Let's look at a few problems now, and let's start with this one here. We're talking about a child sliding down an incline, a 38-degree incline, and the question that's being asked is to draw a free body diagram of the child and also figure out the normal force that is acting on the child. Now, here is a situation where the motion is taking place along an incline. And as I had mentioned, that's the direction of the incline. And as I'd mentioned in a previous lecture, in problems involving inclines, it is much more convenient to orient your coordinate system along the incline, or adapted to the incline. So for example, in this particular problem, it is most convenient if you choose your x-axis, say, along the incline. Well, if you choose that to be your x-axis, remember, you don't have a choice with the y-axis. It has to be perpendicular to the x-axis, so that would be the direction of the y-axis. Okay, and the child is sliding down. So what's the free? So let me put that down as a statement before we proceed. So in problems, and you'll see a lot more of these sorts of problems later on, in problems involving inclines, it is best or convenient to adapt, I'm just going to use the word adapt, your XY coordinate system to the inclined surface. And by this, I mean choose either your x-axis or your y-axis to be along the incline. Okay, if we do that, then, so once we have drawn our x and y coordinate system this way, now to draw the free body diagram, well, one of the forces we are going to sketch the forces. Well, there's always going to be the weight, and then remember, the weight is always in the vertically downward direction. So if you draw the weight, well, the weight acts straight down. The normal force in this case is perpendicular to the incline. Since the incline is along the x-axis, the normal force is going to be along the y-axis. And since the child is sliding down this way, there is the force of kinetic friction, and it's going to be acting in exactly the opposite direction. Okay, so these are the three forces, and I've also included the body that's responsible for each of these forces. Now, of course, the weight is acting in a direction, it makes some angle with the x and y coordinate system, so we have to specify that. Now, if I were to call the angle of the incline theta, which is 38 degrees in this case, so if this angle is theta, now remember the way, if you look at this right triangle here, then this angle is a 90-degree angle, and this angle here would be the remaining, which is what, 52 degrees, okay, because these three angles have to add up to 180. Well, if this is 52 degrees, then this angle is going to be, or in other words, this angle is 90 minus theta, and so this angle here has to be the same angle as the angle of the incline. So the weight makes an angle theta with the negative y-axis, as you can see in this sketch. Okay, so you have to specify that angle. Once we've got that sketch, now we are in a position, again, the approach, the strategy to work these problems is the same as what we've done before. We've got the free body diagram. The only big difference is we have chosen our x and y coordinate system in a way that is convenient for these problems, where the x-axis is along the incline. Once you've got the free body diagram, the next stage is to resolve the forces into components. And to do that, we list all the forces in this first column. We've got the weight, we've got the normal force, and then we've got the force of kinetic friction. Now we got to resolve the weight into its components. Well, the x component is going to be mg sine theta, and it's going to be positive because it's pointing in the along the positive x-axis, and this is minus mg cosine theta. Normal force is acting along the positive y-axis, so that's plus n, and the force of kinetic friction is going to be minus mu sub k times n and 0. Again, I've used the fact that the magnitude of the force of kinetic friction is mu sub k times the normal force. And in this particular case, based on, okay, well, we'll come back. So we got this, we've resolved it. Now you'll see the advantage. What is the question to ask here is, what's the advantage of choosing our axis in this particular manner? Notice in this case, we've got three forces. By choosing our axis in this by sketching our axis or drawing our axis in this rotated manner, notice it's only the force of gravity or the weight which has both an x and a y component. The normal force and the force of kinetic friction are either in the x or y direction. Okay, so there was not much of a resolving that we had to do for these two forces. On the other hand, if we had chosen our axis this way, then you get into all sorts of problems. One of them being it's only the weight which is in the negative y direction. Both the normal force and the force of kinetic friction will have both an x and a y component. And there are other issues as well, and we will soon see that in another part of this problem. Okay, so once we've got that, the next step, of course, is to write down the x and net force in the x direction, which is, of course, just mg sine theta minus mu sub k times the normal force, and the net force in the y direction, which is minus or plus n minus mg cosine theta. Newton's second law says that the net force in the x direction is mass times the acceleration in the x direction. the net force in the y direction, or the y component of the net force is mass times the acceleration, y component of the acceleration. Obviously, the child is not leaving the slide. She's not sliding off it, or coming off the slide, which means we know that the acceleration, y component of the acceleration is definitely 0. So now combining these two sets of results, we have, I'm just going to put it this way, we have, well, to answer this particular problem, in this problem, what they're asking for in part B is how large is the normal force on the slide. So really what we need is, let me take that back. All we really need is the this equation right here. Just focus on this equation right here. And this is to answer part B. And we have n minus mg cosine theta is going to be, again to remind you, I'm combining these two equations, and is equal to 0, or n equals mg cosine theta. Okay, and you can go ahead, you're given the mass of the child is known, the angle is given, so you can actually go ahead and figure out this normal force. So we've got this is that many newtons. One thing to note here is, and I think if you work this out, well, I think I have the numbers here, it's about 178 newtons. Again, notice here the weight here is m times g, and if you work this out, it is 225 newtons, so which implies that the normal force is less than the weight. Again, you can see that from the sketch. The normal force doesn't have to balance the entire weight, but only a component of the weight, okay? And that's why the normal force is less than the weight. Okay. Now, in this problem, one can add an extra part. We've got another equation out here, and the other equation being this equation here, the x component of the net force. And you might say, well, what is that equation good for? Well, here is an additional part to this problem. Suppose the coefficient of kinetic friction is given to you. So if the coefficient of kinetic friction of the child on the slide is mu sub k equals 0.4, determine the acceleration of the child down the incline. So what we're being asked to figure out here is what is the acceleration of the child going down the incline. And let's go ahead and work this out. So what we are supposed to determine here is determine a sub x. So we're going to use this equation, use the net force, and the x component of the net force is mass times the acceleration, or the acceleration in the x direction is net force, x component of the net force over the mass. Now the net x component of the net force, we have an expression, it's right there. So it is mg sine theta minus mu sub k times mg cosine theta over the mass. Well, the mass appears in each of these terms out here, so I can cancel that off. And what we have here is the acceleration is g sine theta minus mu sub k times g cosine theta. And since mu sub k is given in this problem, I've given you the mu sub k to be 0.4. You can work this out, and the acceleration, I think, again, please verify my numbers. Don't take it for granted. So let me just put a little question mark out there. That is the acceleration. Okay, so the child is going to be sliding down the slide with an acceleration of 2.9 meters per second squared. And so there we go. That is that is how the other equation can be used. The other equation, the other equation can be used to determine the acceleration of the child. Now here again, you see the advantage of choosing our axis in this particular manner, because if again we're chosen the axis, if we had drawn the axis this way, then you are, remember, the child is sliding in this direction, so the acceleration is going to have both an x component and a y component, and you'll have to combine that using the Pythagorean theorem. It makes the problem much more complicated. Okay, so and you'll have to figure out the x component of the acceleration, the y component of the acceleration, and work out the details from there. But by choosing our axis this way, we can immediately argue that the y component of the acceleration is 0, so all we need to figure out is the x component of the acceleration, which is down the incline. Now, this is a question dealing with the force of kinetic friction and the fact that the force of kinetic friction actually depends on the normal force. So you've got three identical blocks being pushed across a horizontal surface by a force F. They're identical blocks on identical surfaces. The force F in each case has the same magnitude. So the force has the same magnitude. And the question here is to rank the kinetic frictional forces that act on the blocks in ascending order. Okay. So the key here is to realize that the force of kinetic friction depends on the normal force. Mu sub k is kind of irrelevant in this problem because the two surfaces in contact are the same for all these sketches. So we just have to look at the dependence, determine how are the normal forces ranked. Once we have a ranking for the normal forces, we have our ranking for the force of kinetic friction. So let's talk about the normal force in this situation. And now this is based on what we have talked about, the normal force. Remember, if you're looking at this sketch, here you've got a force F which is directed in an upward direction. Here the force is horizontal. Here the force is pushing down. Okay, so if you're comparing the normal forces, the normal force in sketch A is going to be less than the normal force in sketch B, which is less than the normal force in sketch C. Why? Because in A, this force has a vertical component. The force F has a vertical component, and so the normal force has to balance only a small a part of the weight. You've got the weight in the downward direction. You've got F has a component in the vertical direction, so the normal force is going to be the difference between these two. Here, the normal force is equal to the weight because the force F is in the horizontal direction. Here, the normal force is going to be greater than the weight because the normal force has to not only balance the weight, but a component of this force which is in the vertical direction, vertically downward direction. So here we have the ranking of the normal forces. Once we have the ranking of the normal forces, we can see that the force of kinetic friction is also ranked in the same way. The force of kinetic friction in sketch A is going to be greater than in B, which is going to be greater than in C. So the correct choice here, ranking in the increasing order, it's going to be A, then B, and C. And this another consequence of this, the frictional force being dependent on the normal force, is this situation here. You've got a person has the option of either pushing on a sled or pulling on the sled. Okay, so that the sled moves at some constant velocity. Question is, if the angle theta is the same, does it require less force to push or to pull the sled? Okay, which is going to be easier if you want to do it if you want to move the sled at a constant velocity. So the idea again is a direct consequence of our previous question. So if you push down on the sled, if you push down, then you have a greater frictional force because you have a greater normal force, greater frictional force, and because you have a greater frictional force to overcome, and so a greater pushing force. Since the force that you're going to apply will depend on how much frictional force there is, since there is a greater frictional force in this situation here because you've got a greater normal force, the pushing force is going to be greater. You will require a greater pushing force. Okay? And so in other words, stated differently, it requires a lesser force to pull the sled.